Good morning, good afternoon, and good evening. Welcome to the AI and Machine 5G Challenge webinar series. Thank you very much for sparing your valuable time to join today's session. I'm sure that by participating in today's session, you will gain useful knowledge in solving the problem statement that is going to be introduced. My name is Thomas Baskor from the ITU, and it is my privilege to introduce today's webinar. The AI and Machine 5G Challenge is organized by the International Telecommunications Union ITU, which is United Nations Agency for ICTs. The mandate of the ITU is to allocate frequencies to services that use the radio spectrum, to develop standards, and to assist developing countries in setting up their ICT infrastructure. This challenge is currently sponsored by Xilinx, and we are grateful for their sponsorship. The challenge aims to create a community that will solve network-related problems using AI and machine learning. Now it's time for me to introduce today's speaker. Today's session is going to be given by Adebaro Kratau. Adebaro is a full professor at the Federal University of Para, UFPA in Brazil, where he directs the LASE group and works as the ITU-T focal point. He is also a senior member of the IEEE and the Brazilian Telecommunications Society. His research interests includes machine learning applied to 5/6G and technologies to promote digital inclusion in the Amazon. In today's talk, this talk that he's going to present is going to promote the vision that 5G and beyond will benefit from the availability of virtual worlds to leverage machine learning and artificial intelligence applied to communication networks. As a concrete example for this talk, CAVIAR, which is a communication network and artificial intelligence immersed in virtual or augmented reality framework, is going to be introduced, and he will present RadioStrike. So RadioStrike was developed using Epic Games and Unreal Engine and Microsoft AirSim simulator. RadioStrike is used in the UFPA problem statement for this year's challenge, 2021 ITU and Machine Learning 5G Challenge, in which participants are invited to develop a deep reinforcement learning agent that plays the role of a base station that is serving drones, vehicles, and pedestrians using MIMO beamforming in a 3D scenario. The problem statement targets the participants that are interested in designing machine learning or AI systems that learn from experience and that can outperform conventional solutions relying on signal processing. So welcome, Adebaro, and good morning.
Thank you, Thomas.
Yeah, it is nice that we have you also as well this year for the challenge. So welcome, and the floor is yours.
It's a pleasure. It's a pleasure to be here. Thank you for all participating. I hope that you can see my slides. We are going to cover this topic of reinforcement learning applied to beam selection. This is joint work with Professor Francisco Miller and some of the students at the Federal University of Pará. We are located in northern Brazil, and basically we fight for our sustainable development through science and technology. So we are going to go over some motivation and then talk about the beam selection problem, and finally about the RadioStrike. I'm going to really briefly go over some concepts of reinforcement learning and then talk about the data sets and codes. So if you look at machine learning in the industry, you can see it's part of the studies of most of the standardization bodies, ITU, 3GPP, ETS, Linux Foundation, and ORAN. And if you really look at the papers, you can see that machine learning is still for communications in this small data regime. Basically, the models are small. And when we look at this, let's say, trends that deep learning has of when you increase the amount of data, then you increase performance. Basically, even the reinforcement learning recent papers still have simple models and a small number, for example, of possible actions. So we are facing still this small data regime, in my opinion. And one reason is data scarcity, because if you look at 5 and 6G, then the measurements become more expensive. You have high frequency, high bandwidths, and also multiple antennas. So this traditional way of building, and then we measure, and then we learn, it's really a complicated aspect if you look at this technology. But we have alternatives. And to speed up machine learning for communications, we can, of course, use simulations and then generate large data sets. I liked a lot the ITU Kaleidoscope theme for this year, connecting physical and virtual worlds. And I brought this paper results. It's a recent paper talking about how to speed up this virtual reality rendering, such that you can go, for example, to 200 frames per second. So in my opinion, we are going to be running simulations much faster than real time. And because of that, we should take a look at what's happened to speech recognition. If you look at all the algorithms, for example, the papers regarding the perceptron, the multi-layer, and so on, the convolutional layers, you can see that in 1986, there was a very important effort to create data sets. And this TI-MIT, the TIMIT data set, is an important one from this time. And when you compare, for example, in 94 with the models for 2011, you can see the algorithms were the same, but we basically learned how to use large data sets after we found, for example, how to deal with deep neural networks. And considering, for example, after we entered this large data regime, you could see that for this dataset switchboards, which is very different from TIMIT dataset, we could decrease the word error rate. And when we started using deep neural nets, we got to a performance better than human at some tasks. And what I like to bring is that when in 1986, we started developing the TIMIT dataset, it took 100 to 1,000 hours of work for a phonetician to really transcribe 1 hour of speech. And even they couldn't agree, for example, on in 25%, they were not agreeing on what kind of label they would provide to that piece of speech. So also the cost is something to bring our attention. And what I'm trying to tell you is that at this point in communication, we maybe get to this situation where we invest lots of time and then later find out that's not so all these details are not needed. But if we compare, we still need to go through this large data regime. So if we consider that simulating communications can be done together with artificial intelligence and virtual reality and augmented reality, then we can understand that 6G simulators are going to probably leverage all this information, given that they are going to be dealing with, for example, holograms, and they are going to be transmitting this information and also benefit from that to increase performance of the communication system. So this all requires a new kind of simulation framework, and this problem statement is related to that. As Thomas mentioned, CAVIAR is basically the communication network being simulated together with AI and VR and AR. So you can get details on this paper that we have on archive, but basically consider that we are going to get measurements from a virtual world. So you have, for example, a simulation that provides you the channel and also data, for example, from sensors such as GPS or LiDAR, and then you concatenate and get your model after some learning algorithm. In the test or deployment stage, what we are aiming is that we may not even need the real measurements and simply feed the data from the sensors in the real world and get a good results, for example, for channel estimation and many other problems. Today, we are going to focus on beam selection, but of course, you can use that approach for many other communication problems. And if we consider, for example, what's going on with 6G, when you increase the frequency, then you can pack more antennas. And this is just an illustration, but as you move from one to several antennas in an array, you can find beams imposed, for example, by a vector that can create a compensation for the attenuation that you have in higher frequency by focusing the energy in one specific direction. So this is basically what we use for this problem of beam selection in this analog MIMO architecture in 5G millimeter wave. We want to align the beams of transmitter and receiver, and we have a code book at the transmitter and another one for the receiver. And you can basically pick one of these vectors in the code book to impose a beam, and then the pair of these indices at the transmitter and at the receiver are going to be used to combine with the channel, the actual wireless channel, and basically want to maximize the magnitude of this combined channel. So if we apply brute force, then you have to try all possible pairs, and this takes a lot of time. This is an overhead that we want to pay for. So if you assume you are using a machine learning based approach, then basically, typically we have supervised learning. We pose as a classification problem. In this example, we have just two beam vectors at the transmitter codebook and also two other at the receiver codebook. And if you apply, for example, at the input of a neural network, some information from the communication system, such as received pilots, and also from sensors such as GPS, then you can ask the neural net to tell you the best pair of beams, for example. And what we are going to do is to avoid supervised learning and apply reinforcement learning. Of course, the best may be a combination of both. But now let me talk about the RadioStrike. So if you consider the reinforcement learning, the most popular API is the GEM from this OpenAI company. And basically, it's a very simple API that takes in account that you have an environment, your agents, in our case, for example, it's the scheduling of a user or a beam selection action. And basically, this agent has to give this action here to the environment, and then the environment changes its states, and then the agent can also not only receive the state, but also rewards. And the goal of this agent is to find a policy that maximizes not the instantaneous reward, but the long-term return. So if we have, for example, in our case, episodes, it's not a task that continues forever. It ends after, for example, 3 minutes. Then the task of the agent is to maximize this return over the set of episodes. And if we look at the API, we have the main methods as being the one to create the environment, to reset the environment, to visualize it. And also, this is the most important maybe, to give one step. I'm going to try to provide an example using the card poll. Okay, so this is basically how it goes, a very simple GEM example. You are creating the environment with the make, you are resetting, and then in a loop, you're basically rendering to show these images. And here we are taking a random action. So we are sampling the action space, and then we are giving a step in the environment. So of course, you need to train the agent such that it makes, it has a successful result. And in our case, we want to choose the beam to maximize performance with respect to throughput and packet loss. So we hope to have some kind of good results to get this kind of balance here. So getting into the details of the system model. So basically, the reinforcement learning agent is going to run in the base station. It's performing scheduling of users and also choosing the beam. Each user has a queue, and the agent can know this buffer status. So it can know how many packets are in the queue. And as I mentioned, we are using scheduling beam selection and for the downlink. So you get an idea about the channels because you are simulating, so you don't need to have a hard time on measuring. And you also get information about, for example, the position, also the speed or orientation, and you feed this kind of information because we are interested in finding how this information can be used to help improving the system performance. So this is basically what you can see when you map to this model. The agent, as I mentioned, is assuming this analog MIMO architecture, and there are 3 users to be served: a pedestrian, a drone, and a car. And the agent is going to choose one of them at each time slot, and also choose the beam to serve that user. And the state is something that the participants of the challenge can choose. For example, the state can be the position of the users. It can also include the scatters, for example, cars that are surrounding the receiver. It can also include the buffer status, the previously scheduled users, and so on. So there is flexibility on defining the states, and also you can compose some sort of intrinsic reward. But in the evaluation part, the reward is going to be the normalized throughput with a penalty for dropped packets. So we don't want the agents to allow, for example, this approach of a maximum throughput, such that a user with a good channel gets maximum throughput, but then you penalize the guys that have a very bad channel. So we want to put a penalty for dropped packets. And the return is going to be the summation of all rewards. So some of the research questions and strategies that we adopted were the following. Whenever we are performing user scheduling and beam selection, as mentioned, does this position information help the scheduler? And if it helps, by how much? Can we benefit from knowing the position of the scatters? And from our experience with the previous challenge, we found that we should help the participants to go over this learning curve, to avoid them to give up whenever they find it's too difficult. So besides this main problem, the one that's going to be evaluated, we also discuss simpler tasks. I'm going to talk about the simpler environments. And we want, of course, to keep evolving, such that we are going to build together with the community more advanced CAVIAR games, such that we can create benchmarks and then have this, let's say, large-scale regime really being possible. So I'm going to talk about some of the strategies. And the first one is that we find out that in the deep learning frameworks, there are many options, but also some other specialized tools, such that composing the environment is a problem itself. So if you look at, for example, all the options we have with PyTorch, TensorFlow, Keras, different versions of TensorFlow. And then if you move to deployments, we are not going to address in this challenge, but you have also many tools from Qualcomm, also, for example, the PyTorch quantization that allows us to decrease the size of the model such that it can run faster, and many other tools from NVIDIA, Intel, and so on. And we also need to debug, for example, with TensorFlow, we can also use Jupyter notebooks and so on. So it's not trivial to set up the environments. And we are going to try to, this other strategy is to provide a baseline code, which is simple enough, and that we can provide an environment such that the participants can start by this baseline and later, if they want, move to other advanced or more advanced setups. So this is the kind of codes that we provide. For example, if you have a model that was already trained, you can simply download, for example, in this case, a DeepQ network, and then you can render if you want. And as I did before, reset and put in a loop, such that the trained model is going to predict the action based on the observation or the state of the environment. And then you give the step, which is the most important function, as I mentioned, from the GEM API. And then you get rewards, you get new observation and some information, and also a Boolean flag saying if it's finished or not the episode. And for training, then we also provide some codes that can, let's say, help people to go over all these setups without spending too much time in model selection. So the third strategy was to postpone using ray tracing and adopt a simpler MIMO chain estimation. The reason is that we work with ray tracing for some time, and we want to use the ray mob time methodology to add this machine learning for communication engine here and put all this to work in a loop. For example, you can imagine the drone is being influenced by the decisions made by the reinforcement learning agents. So whenever the drone changes the trajectory, we need to estimate another channel. So if we try to run this in a loop using all these softwares, it runs really slow, at least for our hardware. So we postponed it, and for this challenge, we are going to use a simpler MIMO channel model based on geometry. And this is left for future environments. And as I mentioned before, we are creating not only this environment for the challenge itself, but also a simpler one. And both of them, we are basically using this kind of strategy. We have a base station here in red, we have users in blue, we have scatters, and then you need to choose the user and the beam. Why we are splitting this? This is not gonna be used for evaluating, for example, our participant models, but in our opinion, it's gonna help people to learn about the algorithms in a simpler environment, which is more predictable. Such that in this problem state 6, we are gonna have not only the challenge, but also a learning environment such that people can get familiar with reinforcement learning. And also we want to provide a framework for building future CAVIAR simulations. So I'm just gonna go quickly over some of the concepts of reinforcement learning, just to give you an idea about the things that we want to incorporate in this experience of interacting with the participants in building a community. So if you look, for example, at the simpler environment, you can see it's a grid world. You have, for example, line of sight and non-line of sight situations. And even if it's such a small and very restricted environment, if you take, for example, only 2 users, 64 beam indices, you already have more than 5,000 states. And in this case, 128 actions. So you can see that this grows, the number of states grows exponentially. But for this kind of environment, you can still use a table, and then you can simply find this pair of state action, and for each one, calculate the long-term return. So we want to provide support to people that are starting with reinforcement learning and want to start by the simplest strategies that are the tabular, such that they can construct, for example, using Q-learning, such a table, or even instead of using a full reinforcement learning, using bandits, which are simpler and basically don't have this idea of time evolution. And we are going to also provide support for people who want to start from there. And we map this kind of problem with, that's of course beam selection for telecommunications, with problems that are more, let's say, popular and people can find, for example, in textbooks. And in this case, we need to, for example, to let people know what are the differences between this situation and this kind of grid words, where, for example, you have a policy here and you know at each state what you should do. And this is the kind of technique that we want people to be aware. So if you consider, for example, the rewards in this simpler grid words, in this case, it's -1 everywhere, unless you reach the pink corners. And then you find the Q values. And based on the Q values, you can then find the optimal policy. So we want to help people that are not experienced to try beam selection, but going over all this, let's say, going over the simpler approaches of using tabular methods. And then you reach the situation where you cannot use a table anymore because it becomes too large. Then you start using a neural net. And basically you substitute the table. Instead of having the pair in each entry, you basically feed the network the inputs with the states. So this is the observation that you are getting from the environment. And then you estimate, for example, the Q value. This is the DQN approach. And besides getting the advantage of not having to store things in a table, you also can deal with inputs that are real numbers. So before you were restricted to quantizing a real number, for example, or sticking with discrete states. But here with neural nets, you can feed real numbers there. And then you have many issues that we are going to be using to build more advanced environments. For example, you may not have a balanced data set. Some beams can be more, let's say, popular or can be aligned with the streets and then have a high probability. Also, you can have stationary or non-stationary environments. Also, the state can be fully observable or not, such that why reinforcement learning is not easy, because typically it needs some reward engineering, and we are going to try to provide and let's say collaborate with the participants such that we can build such environment. And another thing for the future is when you try to predict not, for example, a discrete action, but a continuous one. I brought this example for if you consider a power allocation in a cell-free MIMO environment, you need to estimate this real number. In this case, you need to use, for example, policy gradient methods, such that the neural net output is the policy. It's not the Q value anymore. And also, this kind of method supports stochastic policies, such that the state continues to be the input, but the output can be, for example, a real number. In this case, if it's a discrete, you use, for example, softmax activation, and this is a distribution over actions. But if you really need real numbers, then you can model things such that the output are the means and variance of Gaussians, and then you draw from these Gaussians the actual number that you're going to provide as, for example, the power that you estimate. So in summary, it was a very brief review, but basically we want to provide, let's say, a strategy of letting people start from the most basic RL algorithms, the tabular methods, and then move, for example, towards DQN and also policy gradient methods, and the state of art when you combine these two approaches and have two neural networks in this actor critic, for example, such that you stabilize the learning and get better results. In all these cases, the number of output neurons must be the same as the number of actions if you don't do anything smarter. And because of that, we chose a small number of actions for this problem statement. But of course, we want in future to increase and deal with this problem of scaling the reinforcement learning agents. So now talking about the problem statement. So you can see from this figure, this Unreal Engine environments, and you have the base station serving this drone. And maybe I can show you the video. So I hope it works. Then you get an idea about how these things go. For example, you have the drones, but also the cars and also the pedestrians. We are going to choose only 3, taking 1 pedestrian, 1 car, and the drone, and see this is basically showing us that the drone is the one that's being served. But you need to switch and serve also the other users, the pedestrian and also the car. So if you look at this simulation, a block diagram, what we do, we start with a waypoint. It's basically what we use to tell the drone where to go. And then we feed the Unreal, that's also using AirSim, which is a plugin to, let's say, control the drones. And then we generate the episodes, the data, such that the gene environments can bring this information and generate training data for the agents. And of course, after testing, you have the option of only outputting, let's say, the decisions, or rendering and observing what's going on in this environment. So we also paid attention because this Unreal takes some time to run and also consumes memory. So if someone has a computer that's not that fast, it may avoid using the Unreal Engine avoid installing, for example, the graphical parts, not rendering, and then training in this loop without using the Unreal and AirSim. So if you want to get the codes and also preliminary data, you can just look at GitHub. And we provided some of these data sets on this Nextcloud website, and also some information about installation. So just to give you an idea about how the data is currently organized, we separated the data for the baseline from the raw data, from the data that we get from the simulation itself. You can see in this case, this is auxiliary data here at this folder here, and this is the final data, the episodes themselves. So we are calling preliminary because we're still gonna provide the whole training set and also the test set. So for each of these episodes, you basically have all this information for some 3 minutes of an episode. And you have all the code to generate yourself. So a simplified installation, if we're only looking at reproducing the baseline, is to install some package managers such as Conda, create an environment, and we are using stable baselines, but you can use other RL library, and TensorFlow 1.14, Python 3.6, and this is what bothers us. So if you consider, for example, stable baselines, you cannot use a TensorFlow version 2. And that's why I was mentioning that we are gonna try to help people start by the baseline and then evolve. And so after activating the environments, you can run, for example, to train actocritic neural nets and then tests. So about the data organization, we called an episode and we are saving as a comma-separated value text files. And basically they provide information sampling at a sampling interval of 10 milliseconds about the object, for example, if it's a UAV, the position and some orientation information, speed information, such that you have something like that, the timestamp and all this information in different columns. And for the drones, we have the complete information like acceleration, etc., but not for the cars. So you can see that some of the columns are not used for the cars. So looking at this kind of file in more details, you can see that the episode longs for 3 minutes, and we are retrieving at each 10 milliseconds all this information, right? So this is the information that doesn't depend on the agent's decision. But whenever the agent starts scheduling a user, then the state is going to change if you are incorporating, for example, the buffer status as part of your stage. So you're going to deal with the environment to compose your state. But let's say the information that's not dependent on the RL agent decisions are in these files. Another thing that we did for simplifying is that for the baseline, we are not using all the positions of all mobile objects. We are picking only the positions of the 3 users. Don't forget that we are sticking with 3 users. For example, if it's the first UAV, the second car, and the 4th pedestrian. So we can skip all that information and then compose the baseline inputs for these baseline agents. But for the challenge itself, people can use any information that's available. So now about the timeline. So we basically provided yesterday these preliminary data sets and also the baseline reinforcement learning codes. And the reason for not providing the effective training data is that we want to make sure that all these, let's say, research questions that we are asking can be answered by the data. So we are going to be releasing data until we compose the first parts of the training data in July 26th. And then in August or earlier, we are going to finish the training there, such that whenever we reach the submission point, we are going to release the test episodes after people submitted the agents. So the participants are going to train with this training data. They can generate extra data themselves, but they cannot use for training the agents, because we want to restrict, as we did last year, that all the models are trained with the same training data. So whenever the participants are submitting, we are going to be able to, after that, release the test episodes such that the participants can reproduce the results, and they are going to interact regarding the best overall agents. So I think I can stop here, and it's important to thank many people. So besides Professor Francisco Miller, we have many people helping us, and we are basically inviting you to participate and check with us about more details and exchange information to not only participate in this very interesting ITU challenges, but also to learn about reinforcement learning. Thank you.
Thank you so much, Adebaro, for this quite interesting introduction to the problem statement and the challenges, as well as the walk through the reinforcement training. I think it would be quite interesting to see people, maybe someone is new to reinforcement learning, but probably this could be a very good place to learn the ins, starting from the basics up to going just deep diving into the reinforcement learning. So it's quite interesting to have you this year as well. So I'd like to open the Q&A. So I would like to invite my colleague Vishnu. Hello, Vishnu, and good evening for you.
Yeah, thanks, Thomas. Yes, once again, very great effort by our colleagues, Aldabaro and colleagues here. I want to thank them for coming back again from last year and start from there. So my first question is, I'm very curious, what did you learn from last year's challenge, and what are you applying from that last year's challenge here? I remember that last year also you had the same domain, and I remember your collaboration with another university on the channel estimation side. But I want to ask, what did you learn from last year's challenge, and what are you applying here for that?
Yes, it was very rich, because when you consider from a research perspective, any of these problems that we are dealing with, these interesting ITU challenges, is very, let's say, sophisticated. So if you consider a researcher, then you should allow, for example, a very sophisticated approach for generating data and also modeling, doing the feature extraction in a very general way. So this is one thing that's good for a researcher. But if you consider someone who is trying to learn about it, then all that flexibility creates a very steep learning curve. So what we learned from last year was that, okay, this rainbow time methodology is something that we are providing for free, but then the code gets large and not so easy to use. And we thought that at this point, we should try to simplify at least the baseline. So this was one way of, let's say, trying to, at the same time that you provide this flexible environment such that people can do research, can create their own simulations, but you also somehow guide the participants through, let's say, easier steps in the beginning. I believe that was the most important lesson.
Thank you, Aldabaro. Actually, that brings me to my next question. You mentioned many times in your speech that this building a community and collaboration with participants, and I think you gave several examples actually. The Q table example you gave one, and I think the policy gradient you gave another one, which probably points to future opportunities of collaboration. But I want to ask you, what is important in this challenge? What is that the participants can collaborate with you in this challenge? When you say building a community for this particular episode of the challenge, this particular problem statement, what can they collaborate with you to do?
Okay, I think that it's still not clear how we can really benefit from all these rich context environments. We have been publishing about it, and the industry is also giving steps towards not only taking, for example, signals from the communication system itself, for example, traditional pilot tones to get channel estimations, but getting information about, for example, the cars or the speeds and directions, trajectories, and etc. But it's still not clear how to really combine all of them. And for example, you can see people doing channel estimation using the correct channel to train the models. But when you put a model in, for example, a base station, it's going to first to estimate itself the channel because it doesn't have the knowledge of the correct one. So we are kind of dealing with simulations that are still not realistic, and people that don't like much machine learning, then of course they complain about. And I think that's the most interesting aspect of collaborating, is that you come up with an idea, then you can put this idea together with others, such that you can really, let's say, pass this stage of trying, but without this realistic or this convincing kind of result. And this is something that we cannot do alone. I don't believe that one research group is going to be able to put all these things together and really build a very realistic scenario. We should be able to do some sort of effort together to build this framework, and this kind of framework that brings information not only from the communication system, but also from the sensors, such that we learn how to use the sensors. And that would be, let's say, this ITU challenge, a perfect environment to do this sort of collaboration.
Thank you. Thank you, Aldabaro. I want to ask about the collaboration, channel estimation. So yeah, you mentioned about this channel estimation problem. I think you talked about leaving it for future. What did you take from the previous year's challenge with respect to the collaboration for channel estimation, and where would you take it and fit it and integrate it in future? So I'm trying to ask. Let's say if there is another problem statement, and there is another problem statement which is working on channel estimation as such, then how is it possible to take such solutions and integrate it here in future, if you can?
Yes. Channel estimation is a perfect example. If you look at the results from previous year, the challenge that was organized by Professor Nuria Gonzalez Prelchik, the conclusion was that data-driven methods can, let's say, be used in future, but they are still not mature enough to beat the conventional signal processing. If the signal processing adopts something, for example, as Bayesian learning to tune the channel estimation to the priors that are imposed by the environment, they are superior, for example, to deep neural networks, at least At least that was the findings of this challenge last year. And I found it very nice because we are, as I said, we are still finding our way of combining these techniques. And this is one step. If you look at the results, and they are going to publish on the ITU journal, JFET. So if you look at the results, you're going to observe that it's one step ahead. We know that if we tune or if we adapt the channel estimator to the environment, we get much better results by more than 5 dBs, for example, with respect to normalized mean square error. Now, we should not stop. We should not stop from investigating, because from channel estimation, we can do tracking, the channel tracking and so on. But we are not going to be able to beat, in my opinion, the traditional methods if we don't have huge amounts of data. And we still don't have. So we are running tracing simulations for a long time, and now we have maybe the largest data sets on ray tracing. But they are still small if you compare, for example, with the diversity that deployment and actual deployment of a base station has to deal with. And all this description that I did today is related to increasing the realism of simulations and paying attention also to the computational time, such that we don't build something that we pay $1 million, as in that timid data set, and compose something that can effectively be used to answer questions such as, okay, if I try to decrease the pilot tones and make it more, let's say, flexible, what can really be done if we take the context in account? Because when we designed 4G and previous versions of wireless communications, we typically design it for the worst case. And the number, for example, of pilot tones was somehow fixed or limited in terms of flexibility. But as we move towards 5G, you can see now the scheduler becoming more and more flexible. So if you can, you basically taking in account previous decisions or previous information about the channel states, and then use less pilots. So my impression, Thomas, regarding channel estimation is that what I would like to see is taking this kind of environment, this kind of CAVIAR simulation, and then actually putting an agent that can decrease the number of pilots as it learns more about the environment. And in the very end, we may not be able to completely, let's say, eliminate pilot tones, but to decrease the overhead significantly compared to what we have today.
Thank you. Thank you, Aldabaro. I think, let me see if there is more questions. I think I have several more. You know, the steps that you mentioned, I think in your steps strategies, I think you called it strategies. The setup, I think about slide 23, you had this guidance with the setup, and then in baseline code, that is strategy 2 and so on, right? So these is the steps till you provide the detailed data. What can the participant do? So let's say I am a participant. You have this initial data that you have provided. What should I do till with this existing baseline code and data till that time?
Yeah, it depends on how anxious the person is regarding the competition itself and getting the best results for the competition, right? My experience dealing with this reinforcement learning is that many people, they simply give up because the number of degrees of freedom is so large that the agent doesn't converge. So what we are doing when we say we have a simpler environment is to allow people, for example, that are dealing with such algorithms, DQN, and then you have others, A2C, A3C, all of this is available. But when you start using a new problem, it's not that easy to make all these choices if you don't have a very fast cluster of computers or with GPUs, etc. So what we are assuming is that you can, let's say you're willing to play with this A2C and compare with DQN, that you can do that with a simpler environment and get some feedback from us. Of course, they could study by themselves. But when I talk about building a community, is that using the tools that ITU is providing, we could put people discussing things in an environment that's not, let's say, the same as the actual final challenge, the model for the challenge itself. And what I expect is to see them learning in this environment being much faster in terms of computational requirements, such that then you can translate to the more advanced environment without all this pain and people giving up because of no convergence issues.
Thank you, Aldabaro. There is a question. Use situational awareness. Yes. I think I had this question also. To assign best beam, or is it to maximize cell throughput? Does the data include cell level information as well as for example, bandwidth, etc.? So yeah, the first part, the situational awareness, I think I was thinking about the same thing. The objective is only to assign best beam per user. That's one part of the question. Second part is to max, or does it include maximizing cell throughput? Can you comment, Aldabaro?
Yeah, great question. Thank you. I would say it's to maximize the cell throughput across the users. So you should be able to maximize the summation minus the number of packets that were dropped, and we are going to have weights for that. So basically, it's not only selecting the best beam, but also selecting the user. You can pick, for example, given the buffer status, and I didn't mention much, but we need to generate traffic. So we are using Poisson distributions. So assume that you have the traffic coming and you need to pick the user and also select the best beam for serving that user. And regarding the kind of information that you have, you basically have the MIMO channel. You get an estimate of the MIMO channel, and you basically can make also decisions regarding, for example, I would say the whole cell based on all these kind of positions and speed. For example, you can kind of predict the trajectory, especially of drones and cars, such that you can try to incorporate that in your scheduling.
Very interesting. Yes, thank you so much. I think, as you mentioned, it is the three users that you are focusing upon right now. But maybe this can be a thing of like you just now mentioned. You can incorporate other data, and also I think you correctly mentioned earlier that other data, situational data, can be incorporated maybe later, and also the quantization techniques, the optimization and quantization techniques. That's another dimension which is quite interesting and related dimension and problem statement itself, I think.
But for in terms of the deep reinforcement learning, currently we have only this problem statement that is using the RIFL. But I hope in future we have more problem statements that are related to maybe reinforcement learning, deep reinforcement learning, maybe a combination of the different types of methods. As last year, we had a problem statement that uses data-driven approaches as well as traditional approaches. The mix, I think most of the winning solutions were a mix of these two. Do you think in terms of the reinforcement learning, can we combine different approaches to improve the results?
Yeah, yes, for sure. When we were designing this problem statement, we were considering to involve not only reinforcement, but also supervised learning. Because if you consider that you already have data, you can of course do the best that you can with supervised learning if you have the labels. So if you somehow you already got some amount of labeled data, you can come up with an initial model, and then it's some sort of transfer learning together with reinforcement learning, the kind of technique that's going to allow us to adapt to the new environments, such that, for example, a company can distribute basically a model for, let's say, any initial deployment. And then after some time, this model gets smarter and smarter. So if we really want to evaluate this process, we are going to see the need to combine supervised reinforcement learning and so on. We gave up because we thought it could be too complicated for people to deal with both, and then we went in this direction of using only reinforcement learning. But it's for sure something that you're going to see in future, like this combination of different approaches to maximize performance.
Thank you so much, Adebaro. We are already almost time. So I would like to give a very big appreciation for you for joining today and discussing this problem statement. And of course, we would like also to thank your research group for coming up this year to join this challenge once again. I think last year, this problem statement was one of the successful problem statements with some 3 participants who competed in the final event. I believe that this year we are going to see more interesting solutions, more interesting results, more competition. So we are happy to have you on board this year. Thank you so much.
Thank you. It's a pleasure.
At this point in time, I would like to close this webinar. So thank you very much for joining, and we are going to see you in next week. So everyone, I wish you have a good and a lovely day. Bye-bye.